Swayam Prabha. Digital India. Educated India.
Our last topic for this course is the notion of countability and what it means to be uncountable. We'll start with a little story of Hilbert's hotels. This is Hilbert. He might look like a hotelier, but he was actually a very famous mathematician from about a century back. And the hotel that we are talking about is has infinitely many rooms. It has rooms numbered 0, 1, 2, 3, and so on. So all the natural numbers. Okay? And at the beginning, all the rooms are occupied. You could think of the natural numbers, 0, 1, 2, 3, and so forth, as staying in their rooms, numbered by their own number, right? So 0 is staying in room 0, 1 is staying in room 1, and so forth. And then suppose along comes, so there are no vacancies in this hotel. All the rooms are occupied. Now suppose along comes a new guest, -1. Okay, it's not one of the numbers that's already staying there, and it wants to get a room. So instead of turning away this new guest, what you could do in Hilbert's hotel is you could just ask all the guests to move by one room. So number n gets out of room number n and goes to room number n plus 1. And if every number does this, then room number 0 becomes available and you can put the new guest there. Okay, so even though there were no vacancies, you can easily accommodate another guest. And of course, you could keep doing that. You could accommodate one more guest and one more guest. But what if, so you could accommodate any finite number of guests, right? But what if an infinite number of guests arrive? So suppose all the negative integers arrive. Okay, so if you try to do what you're doing earlier, you'll never finish that process because there are infinitely many guests to accommodate. But you could do something else. You could ask all the integers to move to twice a number. So number n moves to room number 2n. And then all the odd numbered rooms would be free. And there are infinitely many of them. And you could put all your new numbers. So minus n, so say minus 1 goes to 1, minus 2 goes to 3, and so forth. So all the odd numbered rooms can be taken up by the negative integers. Okay. So even though the hotel was full, now you could accommodate an entire, infinitely many guests, right? Entire set of negative integers. Now, you might think that, so this of course very strange, but this is how infinity behaves. You can find many infinities within infinity. So you might think that, okay, this is how it's going to be. But what if all the real numbers arrived? Okay, there are infinitely many real numbers. Could you accommodate them in this hotel? And it turns out you cannot. Okay, so there are not enough rooms, no matter how you try to assign the real numbers into these rooms. In fact, even if the hotel was a priori empty, you cannot put your new guests into the rooms in this hotel. Okay, so that's what we're going to talk about today. But of course, we would like to make it all very formal. So, so intuitively, there are more real numbers than integers. That's why these real numbers couldn't fit into rooms numbered with integers. Even though both these sets are infinite. So one infinity is bigger than the other infinity. Okay, so how do we make this precise? And also, when do we say they have the same size? So, so we saw some instances which should suggest, when two infinities were equal, how do we make that formal? Okay, so we'll start with that, and it's a very simple definition. we will say, and so this, these numbers that we're talking about, infinity, that's the cardinality of a set. That's the number of elements in a set. Okay, that's called the cardinality of a set. So we are interested in talking about cardinalities, and we will say two sets have the same cardinality. So they have the same number of elements informally if there is a bijection from A to B. Okay, so this is the definition of two sets to have the same cardinality, or two sets to be of equal size informally. That is, if there is a bijection from one to the other. Okay? This is a definition that works for finite sets also, right? So for finite sets, this cardinality is an integer, is a finite integer. So it does mean something to say, these are equal. So both of them have to be the same number. With infinite sets, the cardinality is not a number, so you cannot say both of them should be the same number, but the definition is that there should be a bijection between the two sets. But the same, if there is a bijection between two finite sets, that's also, that's possible if and only if the two sets are the same size. So this definition of equal cardinality works for finite sets as well as infinite sets. We are interested in infinite sets here. Okay. So as an example, if you took the set of all integers, positive and negative and 0, and on the other, so that's your set A, and on the other hand, you have the set of all even integers. Okay? And these two sets are the same, have the same cardinality. How do you see that? So here is a function from z to z, simply mapping x to 2x. And this is a bijection. Why is this a bijection? Because it's injective. It's invertible, and also it's surjective. Every element in 2z is mapped to by some element in z, right? This is an even integer, so half of that is another integer. Okay, so this is a, according to our definition here, these two sets, the set of all integers and set of even integers, have the same cardinality. Here's another example. There's a set of integers, positive, negative, and 0. And this is a set of natural numbers, so non-negative integers. And they also have the same cardinality. And the bijection, a bijection that you can define is the following. It's something we already alluded to in the hotel example in the previous slide. So you map all the non-negative integers to twice themselves, and you map all the negative integers to the odd numbers that are left in between. So 2 times the absolute value of x minus 1. Okay, and again you can check, convince yourself that it's an injection and a surjection, so it's a bijection. And you can put these two together, so you can compose bijections to get a bijection. So you could say, there's a bijection from set of natural numbers to even integers. So first you map from natural numbers to integers. So that is the inverse of G, so G inverse, and then you apply the function f to map it to even integers. So this would be a bijection from natural numbers to even integers, right? So you can, so this property of having equal cardinality is transitive. If because bijections composed and their inverses are also bijections. So bijections composed to be bijections and their inverses are also bijections. Okay, so that means this relation between sets is a transitive relation. Okay, so now we are ready to define something called countability. So we will say that a set is countable or countably infinite if it has the same cardinality as the natural numbers. So the natural numbers are what you use to count. So say in Hilbert's hotel, you had rooms 0, 1, 2, 3. So you had assigned a room number, an integer to each room. So the rooms are countable. You use this numbering. Every room will eventually get some number, and so it has a unique number, and that number is used uniquely for that room, right? So there's a bijection from the set of natural numbers to the set you are interested in, then that set is called countably infinite. Okay, it's infinite because you need all the natural numbers. You need all the infinitely many natural numbers. I mean, they're all getting used to number the elements in A. So A is infinite, but it is countably infinite. Okay. Yeah, so that's when there's this bijection. And if a set has a bijection, it's not just that its cardinality equals the cardinality of natural numbers, but it's also it has the same cardinality as the set of integers or the set of even integers and so forth. Anything which is countable, so countably infinite. So a countably infinite set has the same cardinality as any other countably infinite set. They all have the same cardinality. So it's just a convention that we are using natural numbers to define countably infinite. You could have used, say, just all integers, for instance. A set is called countable if it is either countably infinite or if it is finite. So there are two ways for it to be countable. Because it's finite, so you just counted it and 1, 2, 3, 4, and you said, okay, there are 10 elements in the set, so it's a countable. It's a set of its cardinality is finite, so that means it's a countable set. Okay? Or it could be countably infinite. So you can number all the elements 0, 1, 2, 3, but you'll never stop. There are infinitely many elements, but every element will get its number. Okay, that's countably infinite. Okay. So intuitively, countable sets are what you would call discrete, what you could call discrete sets. So we never defined, we have been talking about discrete mathematics, but we never quite defined what discrete means. It often could mean, we are dealing with finite sets, but we were equally happy dealing with integers. So a better way to think of what discrete is that we are dealing with something that's countable. Okay, so so we defined this that a set is countably infinite if it is a bijection with the set of natural numbers. Let's try counting a few other sets, right? So what about pairs of natural numbers? So pairs like this. So the n cross n or n square consists of elements of the form 0, 0, 1, 0, and so forth. Now, can I count these points? So a naive way to try and count them would be, so this, you could put them in a grid, right? X-axis and y-axis, and the points, at the integral coordinates, integer x and y coordinates, they define this set n square, in the positive quadrant. And a naive way to count all these points would be to count them. So here is here's our set of all the points here, and a naive way to count them would be, you start by saying, okay, this is 0, this is 1, this is 2, this is 3, this is 4, and so forth. Well, this is not a good way to count this entire set because you'll never manage to come back and assign a number to this element. So this element will never get a number if you start giving your numbers out as 0, 1, 2, 3, and so forth. Okay, so that's not that won't give you a bijection. On the other hand, you could do it in a different order. So you could use this, I'm calling it a curve in the sense that you could go around in this squiggly fashion and trace through all the elements. So you're doing 0 0, then 1 0 0 1, then 2 0 1 1 0 2. So first you counted all the elements which have some adding up to 0, then some 1, then sum of coordinates 2, sum of coordinates 3, and so forth. And in this case, I take an arbitrary element out here. I know I can calculate a finite integer that will be assigned to it eventually, right? Yeah, so as I said, if I try to number them kind of going horizontally, I'll never get out of the first row. So that'll not give a bijection, but this one does. And it's a simple exercise to, kind of drew it as a figure, but you can formally write down what this bijection is. How about z square? So not just sticking to the positive quadrant, but if you have the negative integers as well. Well, so we already saw that z is countable. So there is a bijection from z to n. So we might as well first take this pair of elements in z, map them to a pair of elements in n. So first you apply, so this mapping G is a mapping that is a bijection from z to n. So this applying G coordinate wise gives you a bijection from z square to n square. And then from n square to n, you can apply the bijection here, for instance. And that, composed, they will give you a bijection from z square to n. Okay, so z square is also countably infinite. More generally, if A and B are both countable, then A cross B is countable. So if A and B are both countably infinite, or if one of them is countably infinite and the other is finite, in those cases A cross B is countably infinite. Of course, if both are finite, then A cross B is finite. Okay? And if A and if you have A, B, C, and a finite number of such sets, their cross product, A cross B cross C, and so forth, that would also be a countable set. Okay, so this is good, and I can have creative bijections from infinite sets into the set of integers or natural numbers to show that it's countable. Okay? But sometimes things are a little more complicated. So let's take the example of rational numbers. Okay? So intuitively, rational numbers are like a pair of integers. It's a ratio of two integers. And we already have a bijection from pair of integers to natural numbers. So all that is left to do is to find a bijection between rational numbers and the set of pairs of integers. But it's not immediately clear what's how to do that, because even though, say you're trying to find a bijection from z squared to q, so every pair AB, you could think of it as corresponding to a rational number A divided by B, but it's not an injective mapping. So there are many different pairs AB that map to the same rational number A divided by B. Okay, when A and B have a common divisor. Also, if B equals 0, then you cannot just, A divided by B is not a rational number. Okay, so there seem to be all these kind of annoying special cases that you need to handle to come up with a bijection. You can do that, but it turns out that you don't need to actually explicitly describe a bijection if all you care about is to show that there exists a bijection between Q and Z squared. Okay, so that's what we'll see. So let's start by seeing what we can immediately say. So Q, so on the one hand, it's easy to construct an injective function from Q to Z squared. So in some sense, Q is no larger than Z squared, right? So why is that? So for every element in Q, there is a canonical representation as a pair of integers. Namely, you think of the element x as p divided by q, where you require that p and q do not have any common factors and q is positive. That gives you a unique way to map x to a pair of integers, right? So that's and importantly, if two different rational numbers cannot have the same pair. So given a pair, you can uniquely go back to the rational number you came from. So it's an injector, it's an invertible function, so one-to-one function. And of course, that the fact that you have one-to-one function from Q to Z squared, then you can combine it with a bijection and get a one-to-one function from Q to N, right? So this kind of shows that Q's cardinality in some sense should be considered no more than the cardinality of N, okay? And that is indeed, the non-trivial part, right? Because N is a subset of Q. So clearly N's cardinality is no more than Q's cardinality. So the interesting part to show that they have the same cardinality would be to show that Q's cardinality is no more than N's cardinality. Now we have not quite defined what it means to have a cardinality no more than some other set's cardinality. So let's actually define that. So what we just now saw is that there is a one-to-one function from Q to N, and we thought of that as saying that Q fits inside N, right? So one-to-one function from A to B intuitively translates to saying A's cardinality is no more than B's cardinality, and this is certainly the case for finite sets where A and B are finite integers. So the cardinality of A and B are integers, right? So what we're going to do is we'll just define this notion of a set's cardinality being no more than another set's cardinality. So we'll say cardinality of A less than or equal to cardinality of B if there is a one-to-one function from A to B. So, and this definition works for finite sets also, where for finite sets is we already have another definition in terms of less than or equal to for integers. So this matches the same definition. Okay. So with this definition in place, I can write that the cardinality of Q is less than or equal to cardinality of N. And on the other hand, we also have, because there is this trivial embedding or the injective mapping obtained by the identity function, right, that maps every integer to itself, but as a rational number. So HA, the integer A is mapped to the rational number A. And that's clearly a one-to-one function. So by this definition, cardinality of N is less than or equal to cardinality of Q. Okay, so we have both of these things, and you'd like to be able to say, okay, that means cardinality of Q equals cardinality of N. But unfortunately, that's not as immediate because, I mean, this is just a notation we came up with, right? These are not comparisons of integers. Okay? So we'd like to show that if these two conditions hold, then the cardinality of Q equals the cardinality of N. But unfortunately, what that means is you have to show that there is a bijection between Q and N, whereas what these things give you are injective functions from Q to N and N to Q. Okay. So this is what this theorem does actually. There is a theorem due to Cantor, Schroeder, and Bernstein, which says exactly this, that if there are sets A and B, and if there is a one-to-one function from A to B and a one-to-one function from B to A, then you can somehow put them together and get a bijection from A to B. And conversely, of course, if you have a bijection from A to B, that would work as a one-to-one function from A to B, and the inverse of that bijection will work as a one-to-one function from B to A. So if there is a bijection from A to B, then both these conditions hold. What the non-trivial part of the theorem is to say that if these two conditions hold, if there exists some completely different injective functions from A to B and B to A, they need not be surjective functions. So they are not by themselves bijections. Then somehow you can put them together into a bijection between the two sets. Okay, so in terms of our notation that we just now had, if the cardinality of A is less than or equal to cardinality of B, and the cardinality of B is less than or equal to cardinality of A, then the cardinality of A and B must be equal. Okay, so that's a non-trivial direction. Now this is, of course, again a true statement for finite sets, but there it's immediate from properties of integers. If x less than or equal to y and y less than or equal to x, then x, if and only if x equals y. Right? But the non-trivial part is for infinite sets A and B. Okay, so here is how we would prove this. Suppose you are given two injective functions in the two directions, so A to B and B to A. Let's visualize this as a bipartite graph. So all the nodes on the left are the elements in A, these are all the elements in B, and the function f could be represented using these edges from left to right. So every node on the left has an edge leaving it because it's a function from A, and every node on the right has at most one edge entering it because it's a one-to-one function. But there could be nodes which do not have any edge coming into them. Okay, so that's f, and similarly have a function g in the other direction. Every node on the left has an orange edge leaving it, and every node on the left has at most one orange edge coming into it. And what we are interested in finding is a bijection, which is, you could think of it as a perfect matching between nodes on the left and nodes on the right. And the way we are going to do this is actually find a perfect matching in this graph. So if you thought of this graph without the arrows, so as an undirected graph, so then there's a infinite bipartite graph, and what we are going to do is find a perfect matching in this graph. Every node will have exactly one edge. So every node on the left will have exactly one edge, and that would match it with exactly one node on the right. So that's a bijective function. Okay, so that's what we are going to do, find a perfect matching in this infinite graph. How are we going to do that? We are going to do that by partitioning the graph into a bunch of chains, and within each chain we will find a matching. Okay, so imagine you pick an arbitrary node, say here, and then you follow the arrow. So it's a node on the left, so you know that it has an outgoing green edge, so you follow that. You get somewhere, you know that now it has an outgoing orange edge, you follow that, and so forth. Okay, and you won't get stuck in the sense that whenever you reach a node, you know it has to have an outgoing edge of the other color, so you can just follow. So this is going to be a chain with alternating colors of edges, and you'll not get stuck. Okay. However, you could cycle, you could have an even length cycle in this graph. So you'll either get infinite chains or cycles. Okay. Uh, Now, so these still refer to them as if they are chains. So this partitions the graph into a bunch of uh, chains. So no node can be part of two chains, because indeed, given a node, I can uniquely trace the chain, kind of going forward, and I can also, since it's one-to-one, I can uniquely trace the chain going backwards from this node. So, given a node, there is a unique chain that it can be part of, and there is a chain. So, maybe there is nothing coming into this node, but there's always something going out of this node. So this is part of some chain. Maybe there's the first node in the chain. It might be starting from this chain node, but every node is part of some chain and exactly one chain, right? All right, so we have partitioned the graph into chains. Some of these chains could be actually cycles. Yeah, and so here is what I was saying. So you could go backwards, and given a node, you can uniquely find the chain it's part of by going forward and backwards uniquely. Okay. Now, so again, to repeat, the fact that I could go backwards uniquely use the fact that it's a one-to-one function. The orange function here is one-to-one, so there are no two nodes coming into it. I may not be able to go backwards if there's the end of the chain, or the beginning of the chain rather, but if I can, then there's a unique way in which I can go back. Okay, so now there are three kinds of chains. So there are infinite chains that start from a node on the left. So for instance, here the chain that this node is part of, since it does not have an incoming orange edge, there's a chain that will start here. Okay? And then this chain will keep going on forever, right? Since it cannot cycle back to this node, and it can never end, because it's always you'll be able to find, from the left you'll have outgoing green edges, from the right you'll have outgoing orange edges, so the chain never terminates. So that's one kind of chains which start at an A node and they are infinite. Similarly, there are chains that start at a B node and they will also be infinite. Now, there can also be chains which do not have an end or a start. These are infinite in both directions. So there could be chains of that form. And also there could be finite chains, in which case they're not quite chains, they are cycles. Okay. So these are the four kinds of chains. So I've called three kinds of chains here. So chains which start at A, start at B, and the other kinds of chains, so which are doubly infinite or cyclic. And I'm going to find a matching in each of these cases. So when it's a cycle or a doubly infinite chain, you can find a matching by arbitrarily including one edge in your matching. Say you pick an orange edge, then you just pick all the orange edges. Okay, that will give you a matching of just the nodes that are in the chain can all be matched with each other. So if it's an infinite chain and you pick all the orange edges, that'll give you a matching of all the nodes, right? It's a perfect matching. Similarly for cycles. But if it's a chain that starts from an A node, so A-type chain, so a chain that starts like this, if I took all the orange edges, then this node will be left unmatched. Okay, so in this case I have to pick all the green edges. But if I pick all the green edges, I'm good, because every node in this chain will have a green edge going out of it, or every node in the going out of it or coming into it. because that's how I, you know, got to that. So you take a node on the right. The reason it's part of this chain is because I arrived at it through a green edge. That's true for everything, and every node on the left, I left it from a green node. So it's true for every node in this chain except the starting node where I did not arrive by anything. But since that's a node on the left, I do have a green edge leaving it. Okay, so for A-type nodes, I'm going to pick the green edges, and for similarly for B-type nodes, I have to pick the orange edges. For the C-type nodes, I could pick either the green edges or orange edges. Okay, so that is going to give me my perfect matching. So what I've done here is I said for A-type chains, I'm going to pick the green edge. So I would, so my function will map A to f of A. And for, so function is defined as from A to B. Okay, and for the others, so either B-type chains, nodes in B-type chains or nodes in C-type chains, I'm going to pick the orange edge, which means I have to take the orange edge, but in the reverse direction. So that is, this should be G inverse A. Okay, so A is mapped to G inverse of A. So it's mapped to some B such that GB equals A. Okay, so so there's actually a very powerful technique or theorem to show that two sets have the same cardinality without having to explicitly give a bijection. So the bijection gets defined by, so you just show two injective functions in each direction, and the bijection is implied by the CSB theorem. So so now we can apply this to the problem we were looking at to show that the set of rational numbers is countable. So we saw both these things, and by the CSB theorem, we have that there is a bijection between rational numbers and integers or natural numbers. Okay. Or in other words, the set of rational numbers is countable. Here's another example. Let's consider the set of all finite length strings made of some characters. So say the characters in the English alphabet, the uppercase character. So A to Z. Okay. So there are strings. There is one string of 0 length. There are 26 strings of length 1, and so forth. Right. So any finite length n, you have 26 to the power n strings of that length, and they're all part of this set S. Now this is an infinite set because I can keep going, right? You can keep picking strings of longer and longer length, or bigger, larger and larger length. So it's an infinite set, but I'm claiming that the set is countably infinite. Okay. Now, if I were to directly try and give a bijection, it's kind of a messy bijection to describe, but I'm just going to directly use I'm going to use the CSB theorem instead. So I would say, okay, here's an injective function from S to N. Okay, so this kind of the non-trivial direction. I'm going to interpret this A to Z as integers 1 through 26. So think of them as the non-zero digits to the base 27. Okay, so there is no 0 here. 0 is a digit, doesn't show up in this set A to Z. And now I can think of the string, any given string, finite string, as an integer returned to the base 27, in which only non-zero digits appear. Okay, so clearly not all